So thanks for coming to the temporal graph reading group, everyone. So today we are very glad to welcome Przemysław, who is from University of Oxford and Queen Mary University of London, UK, and he is a postdoc and senior researcher in the group of Ian Horrocks and Bernardo Grau at the Department of Computer Science at University of Oxford. He received his PhD in logistics in the Institute of Philosophy at the University of Warsaw. Um, and his research is devoted to designing methods for reasoning, studying their computational properties, and developing efficient reasoning algorithms for them. He is especially interested in methods for complex reasoning about time, as time is ubiquitous in our daily lives, in the way we perceive and reason about the surrounding world, as well as how our AI algorithms to conduct it. Um, and yeah, so I will hand the mic to you to start the presentation. And thanks for joining us today.
Thank you very much for the introduction. So let me try to start with sharing. Okay, so I hope you can see the screen. Can you?
Yeah, we can see the screen.
That's perfect. Okay, so this is a joint work with Michael Rawson, who is actually with us there, and who is mostly responsible for all the nice experiments. So if you will have any questions, I hope that he will be able to answer all of them. Myself was more into the theoretical part of the paper. So mostly I'm from Queen Mary actually now, where I'm associate professor, and this is my main affiliation, as you can see. Michael Rawson will also be moving to Southampton, to UK, as a professor soon. And this work is about expressive power of temporal message passing. So this is a theoretical work, I would say, or at least research questions from a lens of a theoretician about expressive power of graph neural networks who perform reasoning on temporal data. Sorry, yes, temporal data, exactly. So just let me put it here. So what we'll be looking at are graph neural networks which work on temporal graphs and which perform computations using message passing. So this will be MP, TGNNs. And the idea about them is that we have some temporal graph like you have on the picture, which tells us what kind of events, binary relations, hold in different time points. And then this graph neural network will perform a fixed number of iterations of message passing by modifying embeddings, so vectors, internal representations of those nodes in our temporal graph. And finally, after this fixed number of iterations, it will output the same graph, but with new embeddings. And these final node embeddings can be used to classify nodes, classify graphs, predict some missing edges, and so on. So this is very useful, for example, in recommender systems, if you would like to ask if there's a missing link, so a recommendation between agent and some movie, let's say Netflix, or traffic forecasting or finance networks. So for example, you would like to know which accounts in your financial system are fraudulent or which are not, modeling the spread of disease and many, many more. So this is the type of models that we will be considering. I will provide a more proper and precise definition in next slides. If you have any questions, please stop me. Now, the observation that we have is that there are two ways, at least two ways, but two which occur very often in this MPTGNNs of passing messages between nodes. And we will call them global and local. So the global one is the one presented here. Let's look at these temporal graphs now as snapshots. So on the left side, we've got this input temporal graph, which has 4 snapshots. In each snapshot is a static graph itself. And then in global message passing, what happens is that if you want to compute embedding of a node, I don't know if you can see my cursor, I hope you can. So for example, in this G3 graph, if I have node A and I would compute its embedding, then information which is passed to this node, which is used to compute this embedding, is information from all nodes which were connected to this A in the past. In this case, only B was connected to A in the past, so it means that from B I can pass message to A, which is presented on the right side with this blue arrow, and this is information which is used to compute new color, new embedding of A. This is also called temporal embedding TGNNs in one of the papers recently. It's used in some models as TGAT or NAT. Another way of passing these messages, which we'll call local here, is that if I would like to compute embedding of the same A in G3, I will also look at nodes which were connected in the past to A. In my case, it's also B, it's the same graph, so only B was connected to A. But instead of passing message from this B in time point T2 to A, I will now pass message from B in the same snapshot. So this is what is represented by this blue arrow on the right. So this is a route of message passing in local MPTGNNs. And this is, for example, used in TGN or TDGNN and other models. Let me emphasize that this is a part of those models. It's a way of passing messages. Those models also have some other components. But what we are looking here is at these two different types of message passing. And so the research question that we ask is, what is the relation between these two? So in particular, what tools can we use actually to analyze formally expressive power of these two different types of message passing? What are the limits of those message passing? And what type, global or local, can express more? And finally, also, we looked at experiments. So we asked also this question, what's the difference? How does this difference in expressive power affect practical performance of models? In terms of contributions, what we did is we did 4 things. So the first one is we characterized expressive power of both global and local message passing mechanisms using Weisfeiler-Lehmann test. The idea is that if I have the input temporal graph, I will construct from this at first knowledge graph, one on the top, which corresponds to global message passing mechanism, and one on the bottom, which corresponds to local message passing mechanism. As you can see, these are different graphs. And then to each of those, I can apply Weisfeiler-Lehmann test on knowledge graphs, which was recently introduced. And this Weisfeiler-Lehmann test will color my nodes. And then what we can prove is that if two nodes have different colors in this coloring obtained by Weisfeiler-Lehmann test, it means that my global, if we are on the top part, or local, if we are on the bottom part of the picture, message passing mechanism can distinguish these two nodes. Otherwise, if the colors are the same, then it means that GNN cannot distinguish them.
Just a quick question on this, and sorry to interrupt. So what is the main difference between the global and the local? So we can see there's some clear differences, but just in more detail.
So let me postpone it because I will have a formal definition. It's just the beginning, okay? But
Okay.
You will see a formal definition of this, so I hope it will clarify everything. I would just like to at first say what we are aiming for and what we will get, and
Okay.
then maybe I think it will be clarified.
Okay, sounds good. Thank you.
At the moment, maybe it's important to know that there are these two different ways. I will precisely state what is the difference in a second.
Okay, thanks.
So why is it important is that we obtain this tool which allows us to now formally study expressive power. And the second point, what we did is we used this tool to show what is a good, or at least appropriate, notion of isomorphism between temporal graphs, which would fit the setting of message passing temporal graph neural networks in a sense that it's an isomorphism such that if two graphs, two nodes are isomorphic, then none of these models will be able to distinguish them. The third thing that we did is using also this tool that we have, so using Weisfeiler-Lehmann test on particular knowledge graphs, we were able to compare relatively expressive power of different types of message passing GNNs. So in particular, we showed that the global message passing GNNs, if I feed them with arbitrary temporal graphs, are incomparable in terms of expressive power with local MPT GNNs, which means that there are some nodes which can be distinguished by global but not by local, and vice versa. So none of them is more expressive. On the other hand, if you look at temporal graphs which are color persistent, how we call them, meaning that in the beginning, the input graph which you are given do not have changes in colors between nodes in different time points, just in the beginning. So this is kind of a subset of all temporal graphs that you could consider as inputs. Then the situation looks a bit differently, namely local MPT-GNNs, which I think is quite surprising, are strictly more expressive than global ones. And we have this full picture of results, as you can see. And finally, we did some small, very toy experiments to see what happens in practice. Is it really the case that this expressive power results somehow transfer to practical setting? So this is what we did, and now I will try to set the scene and define stuff properly to, I hope, also answer this question about local and global message passing. So at first, what is the input to our models? It will be a temporal graph, and we will be looking at temporal graphs in snapshot representation. So for me, temporal graph will be a finite sequence of graphs, static graphs with undirected edges, without edge labels, with nodes which are colored. And each of those graphs will be equipped with time points, T1 to Tn. Those will be real numbers. So this is what you can see in the picture below. One assumption is that all these time points are different and they are in increasing order. And the second assumption is that each of those snapshots have the same nodes. So the same vertices. Vertices are shared through all the snapshots. I don't think those are important assumptions in a sense that probably everything can be proved in a similar way if we don't have these assumptions, especially the second one about having the same vertices. However, now we are considering the most basic and the simplest to study setting. So now the models. What models we consider? We consider models which will compute embeddings for nodes V in layers L in time point T. So each model will have a fixed number of layers, and for every of those layers, for every node, and for every time point occurring in a graph, it will compute this value. This will be some vector. So initially, as you can see in the first line, it is set to some color, so the initial color which was in my input graph. And then in every next layer, it will use the second equation in order to update colors. So this update is done in the standard aggregate update or aggregate combine fashion, in a sense that if I would like to compute the embedding in time point T of my node V in layer L, then I will compute it by at first looking what was the embedding of this particular node in a previous layer. And I will combine this color or this embedding with some combination function. I'm on a very high general level. I'm not even saying what kind of function it is, with this part on the right. And this part on the right is information which is taken, aggregated from all the neighbors of the node for which I'm computing the embedding. So the important part is to understand what is on the right side, which I marked. So what is the information which is taken and aggregated and used to combine the embedding? So first of all, what I'm computing this aggregation over, so I'm computing this over all temporal neighbors of VT, of node V and time point T, for which I'm computing embedding. What is temporal neighborhood? Temporal neighborhood of VT will be all timestamped nodes UT prime, such that there was sometime in the past an edge between U and V, and this T prime is exactly the time point when this edge occurred. So this is my temporal neighborhood. It's a standard definition. It is how it's used in TGNNs. And this is the same in both local and global. Moreover, now we need to look what we are aggregating, what we are using really to update these embeddings. So the right component is this G is some function which takes the temporal distance between a node for which I'm computing embedding and the node which is my temporal neighbor. So between T and T prime. This is some function. It's again the same in both local and global MPDGNNs. What is different in those local and global models, and this is where the most important part lies, is the star. So this is an element which will be different in global and local MPTGNNs, and it is defined in the slide. So in global message passing, what we use for this aggregation is we use embedding of u in time point t prime. So I'm looking at my neighbor u t prime, and I'm taking embedding of this u in this t prime, which seems to be quite natural approach. In local, however, the only difference is that I don't take embedding at time point t prime of my neighbor, but at time point t. So this is a little bit of, let's say, cheating. So I'm not taking the embedding of temporal neighbor in the time point where this temporal neighbor occurs, but in my current time point. This is the difference. So maybe I can show you also some pictures which will make it more clear. So this is what you have seen already in the beginning. This is global MPTGNN. Now you have written down below this equation which tells me how to update embedding. So again, if I look at this A in G3 on the left side, if I want to update it, I'm aggregating information over all temporal neighbors. What is temporal neighbor of A in the T3? It's only one, namely B at T2. This is the only node which had in the past edge to A. So this is why in global temporal message passing, I will use embedding of B at time point T2 and pass message to A in time point T3. The situation is very different in local setting, in the setting of local message passing, because now if I'm looking at A in time point T3, again, I'm aggregating over all temporal neighbors. Again, I have only one temporal neighbor because temporal neighborhood has the same definition in both models. It's B at time point T2. But the difference now is that I'm not using embedding of B at time point T2, but I will use embedding of B in the same time point as A, in this case T3. So this is why I have this edge here from B to A at time point T3. So this is the main difference, and you can see on pictures that the difference corresponds to the fact that in local message passing, I have arrows only between elements, between nodes in the same snapshot, whereas in the global setting, I have arrows which go between different snapshots. This is the essential difference. Is it clear now, or any more questions, Andy, to make it more clear?
Yeah, I think it's clear to me now. I think it's more about which embedding you are propagating over time. But I think there's a question from Pharma. Please go ahead.
Yeah, actually, I wanted to see whether the neighborhood sampling is the same. So you just use different embeddings, but the neighbors that are sampled are the same, right?
So yes, that's a good question, and the answer is yes. The neighborhood is the same, but you are taking different embeddings. You could probably rephrase it by saying that you redefine neighborhood for this local message passing without changing then this t into t prime. So probably I could redefine neighborhood and present it in a different way. But in this presentation, the neighborhood is the same, but I'm taking embedding from different time points.
Thank you.
So this is the difference between these two, yeah?
Yeah, and just and I guess something maybe you will talk about later, but what happens if you do both? Do you get a strictly better model than both?
Okay. This is a very good question, which actually we didn't do, and I will not tell you about it. So
Okay.
this is a way to obtain something which has more expressive power than both of those, of course. So in terms of expressive power and in terms of theory, of course, you will have more, right? Because you do just two things in parallel or together. I have not seen any model which does in practice these two things together. We didn't check what happens in practice if you do these two things together. I think, yes, it would be interesting, but maybe a little bit counterintuitive. I don't know. We just consider what is done in literature, to understand what is the difference between what is done already, I would say.
Makes sense. Thanks.
So exactly, this is our question, right? So which message passing mechanism is more expressive and how can we determine it formally? This is what we asked ourselves. And for this, there is a tool called Weiss-Farley-Lehmann test. This is what was used for GNNs to show what is the expressive power of GNNs, and this is what we'll use. So just a short recap of what is Weiss-Farley-Lehmann test. This is a test, actually quite old test, which is the heuristic, I would say, for checking isomorphism of static graphs, which is one of the first steps in most of the algorithms checking isomorphism. So if I have two graphs like on the left, they are static graphs now. I would like to check if they are isomorphic. In this case, they are not, as you can see. I can use Weiss-Farley-Lehmann test. What it does, it iteratively computes colorings of these nodes. At first, in iteration number 0, it assigns to nodes colors which are in the input graph, if it had colored nodes. Otherwise, it just puts all of those to the same color. For example, if they had no colors, as in the picture in the beginning in iteration number 0, they all become, let's say, red. And then there is the step which says how to compute the next color of nodes. So it says that I will use some hash function, it's injective function, which depends on the color of my node in the previous iteration and colors in the previous iterations of all neighbors of this node. And now I'm looking at just standard neighbor of static graph. So in the picture, as you can see, for example, this node number 1 in iteration on the rerun number 1 has a color which is computed based on the previous color of 1, which was red, and the multiset of its neighbors, so two other red nodes. A on the right, as you can see, also had in round number 0 color red, and it had two neighbors of color red. It means that in round number 1, 1 and A need to have the same color. In this case, let's say this is blue. And actually, if you look closely, each of those nodes except B was red and had two red neighbors. So all of those will be colored blue except B, which is green, because it had 1, 2, 3, 4 red neighbors. So then Weiss-Farley-Lehmann test, what it does is when it detects that there is a difference like that in some of the rounds. So on the left, I have 5 nodes which are blue, on the right only 4, then it stops and it says that these two graphs are not isomorphic. And if this test distinguishes graphs in a sense I was explaining, that it means that they are not isomorphic. The other direction, however, does not hold. This is just a heuristic, so it's not precise algorithm for detecting isomorphism. And you've got example of two quite complicated, I would say, graphs which are not isomorphic, but WL cannot distinguish them. Why is it important is because we know quite a lot about WL itself. And in 2019, there was this nice connection of WL with GNNs. Namely, these three statements, actually several more, if you would like to add, are equivalent. For example, two graphs are distinguishable by WL exactly if there exists some GNN, static GNN, which accepts one but not the other, which happens exactly when there is a formula of logic C2. This is first order logic with two variables and counting quantifiers, which is true in exactly one of these two graphs. I will not use logic there, but I'm just observing that there is a very nice connection also to the logical world. One last thing I would like to tell about WL is that recently there was introduction of WL over knowledge graphs. So knowledge graphs are graphs which are multi-graphs, so I can have several edges between the same pair of nodes. Edges are directed and moreover they are labeled. So they are colored or they have some names, some relations. And then a very analogous way of constructing WL, as you can see on the slide, is proposed. The difference is that now I'm not aggregating over neighbors, but for every type of edge, for every R, for every type of relation, I aggregate through neighbors of this type separately, I would say. And this is how I differentiate between different types of relations, different types of edges. And it was showed, it was a paper from 2023, that you can, if you apply this WL called RWL, relational WL, then the distinguishability power is exactly the same as for GNNs working on this type of knowledge graphs. And we will use this relational WL. This is why I'm stating this here. Okay, so now we would like to have WL for this message passing TGNN. So how we do this? The idea is that if I have temporal graph, I will construct knowledge graph. If I'm looking at global message passing, I will construct this knowledge graph, as you can see on the top. So with edges corresponding to ways how messages can be passed. And moreover, these edges will be labeled with numbers, but you can think of them as just colors. These numbers will correspond to the distances between nodes. So for example, this node is in distance 2 from this node. So this is why this edge between them will be labeled by 2. I will not give you a precise definition. It's in the paper. If you would like to have a look, I hope that we can understand from the, let's say, intuitive point of view, not to have too many symbols on slides. In the terms of local GNNs, we do the same. However, the graph looks differently. So this message passing roads are different, and this is why also these edges occur differently there. In particular, edges are only within the same snapshots, sorry. So this is the first thing. I'm constructing these knowledge graphs. And now why these knowledge graphs are important is because I can show how WL on this knowledge graphs corresponds to expressive power of TGNNs. So first of all, I can show that whenever relational WL on this global knowledge graph that I constructed gave me the same colors of two nodes, it means that these two nodes need to have the same embeddings computed by any global TGNN. What does it mean? It means that TGNN cannot do more than this WL on this knowledge graphs. I can have also the other direction. So I can show that for every temporal graph and for every number of layers, I can construct a global message passing TGNN, which will do not less than WL. So in this sense, I have a very similar setting as in a standard correspondence between static GNNs and WL. I precisely characterize their ability to distinguish nodes using WL. But now I'm using WL on a knowledge graph, which is constructed from temporal graph in a particular way. And a very similar thing can be showed for local message passing mechanisms. So the only difference is that now I'm using the local knowledge graph. But other than this, both applications can be proved a little bit differently, but again, I will not go through proofs, but it's in the paper, but we have the results established formally for all of these implications. So what we obtain out of this is that whenever I have a temporal graph, and I'm interested what is expressive power of global message passing, if two nodes can be distinguished by some global message passing GNN, I can construct a knowledge graph, the one on the top, and then I can apply WL, relational WL, and I can see if two nodes, which I'm interested in the end of this WL test, have different colors or the same. This tells me exactly if there exists some global MPT-GNN which distinguishes them or not. And the analogous thing for the local MPT-GNNs, the only difference is that I'm working on different knowledge graphs. Knowledge graph, which looks like the one below. So this is the tool that we have for studying expressive power. So how can we use it and what did we use it for? So first of all, for studying temporal isomorphisms. So what is a temporal isomorphism? This is a question. So GNNs can distinguish some graphs, but not all graphs. So they can distinguish exactly those graphs which are WL distinguishable. If graphs are isomorphic, they cannot distinguish them. So we would like to have some analogical result for MPT-GNNs. We would like to show that MPT-GNNs cannot distinguish non-isomorphic temporal graphs. But the question then occurs, what is the good notion of isomorphism between temporal graphs so that this property will be satisfied? One of the notions which seems very intuitive, and actually we found it also in literature used for something, is what we call pointwise isomorphism. So we will say that two temporal graphs, this one and this one, are pointwise isomorphic if the following holds. The time points are the same in both of the graphs, so each ti is the same as ti prime. And moreover, between each pair of graphs, of the static graphs, in the left and right temporal graph, I will have isomorphism. So in particular, G1 needs to be isomorphic to G1 prime, G2 needs to be isomorphic to G2 prime, and so on. So then the question is it a good notion? It seems quite intuitive notion of temporal isomorphism. And the answer is not, and we can show with our tool that it is too weak notion. Why is it the case? Because we can show that both global and local MPT-GNNs can distinguish those temporal graphs, which are some of those temporal graphs, which are pointwise isomorphic. And here you have a very simple example. So I have two graphs, temporal graphs, on the left and on the right side, and they are pointwise isomorphic because they've got the same time points, T1 and T2, and G1 on the left is isomorphic to G1 prime on the right, as well as G2 on the left is isomorphic to G2 prime on the right. So let's look at two nodes, A at time point 2, so this one, and A prime at time point 2 on the right. So I can have an isomorphism which connects these two nodes, so I claim that they are pointwise isomorphic. But now I will show that I can have actually a global MPT-GNN which distinguishes them. It's not hard to do this. Namely, we can use our approach to construct a knowledge graph which corresponds to the message passing mechanism in global MPT-GNNs. This is on the bottom pictures. And now we can see that if we apply WL to these knowledge graphs, we can see that A on the left will be distinguished by WL test from A prime on the right. And the reason is quite simple, because A on the left has some incoming edge and A prime on the right does not have a single incoming edge. So WL needs to distinguish them. So and we can have also an example for local MPT-GNNs, which also can distinguish these two graphs. So this is not a good notion. The question is, what would be a better notion of time-wise isomorphism? And this is what we introduced. We came up with this definition in which the first property is weaker than the one in the previous definition. Namely, we don't need that all the time points are the same. What we need is that time distances between consecutive time points are the same. However, the second item is stronger than in the previous definition. In the previous definition, we said that each pair of graphs, G1 and G1 prime, for example, need to be isomorphic. Here we say that there exists one function between nodes in one graph and the second graph, which is isomorphic, which is isomorphism for all the graphs. So the order of quantification is different. Before we said that for every time point there is isomorphism. Now we say that there exists a function which is isomorphism for all time points. And it turns out that we can prove that this notion of isomorphism satisfies at least the property given in this theorem, namely, if two time-stepped nodes are time-wise isomorphic, there's no way that any global or local MPT-GNN will distinguish them. This is what we wanted. So this allows us, let's say, to have this notion of time-wise isomorphism. The next step that we did is we studied relative expressive power between MPT-GNNs, and the results that we have are here. So we showed that, quite surprisingly, these global and local mechanisms are incomparable. One could think that this global mechanism allows us to go through different snapshots, so maybe it's more expressive than this local one, which only allows us to pass messages within snapshots. No, it turns out that each of those mechanisms can do something which the other cannot. Another interesting observation is that if I have temporal graphs in which initially every node has the same embedding in all time points, but just initially in the input temporal graph, we call them color persistent, then actually local mechanism is more expressive than global, which can be kind of counterintuitive. So I will not show the full proofs, but I can sketch some ideas there. So first of all, we can show that global is not more than local message passing. So I will show that some nodes can be distinguished by local, but not by global message passing. And then I will also show the reverse direction. So look at these two graphs, and let's consider A at T2 and A prime at T2 prime. What I do first is I construct knowledge graphs again, because this is my tool. For global message passing, this is on the top part of the picture, and for local, which is on the bottom. If I apply WL to this global knowledge graphs, which I have on the top, I can see that this A at time point T2 cannot be distinguished from A prime at T2 because the structure looks the same. So you can simply write down how WL test will work on those, and you will see that they will have the same colors. Both of them have only one neighbor, which is B, and it has also one neighbor, which is A, and all the numbers are the same. WL cannot distinguish them. However, in the local case, we can see that it's different. Namely, this A has a path of length 2 to C, but A prime on the right does not have such a path, which means that if I run WL on these two knowledge graphs, A and A prime will have different colors. So local MPTGNs can distinguish these two nodes. So the result is that it's not the case that global is more than local in terms of message passing. And similarly, I can also show that local is not more than global. So again, I can have two knowledge graphs. Now I think I will be looking at this B node and time point T4. And I do similar thing. I use my tool, namely I apply my approach to construct knowledge graphs, global and local. Local on top, global on the bottom now. And I can see that this B at time point T4 looks in the same way from the perspective of WL test as B in time point T4 on the right. If I apply WL test on these two top knowledge graphs, these Bs will have the same colors, which by our proof means that there is no single local MPTGNN which can distinguish them. But in terms of global MPTGNNs, there is some MPTGNN which can distinguish them, because if I look at this knowledge graphs, B here has one neighbor, A, which is green, and the distance between them is 2. However, on the right, B has only one neighbor of distance 2, A, and this is blue. So because of this, WL will distinguish these Bs and will assign them different colors, which means that there is a global MPTGNN which can distinguish them. And we've got some more proofs which also complete this picture, but I think I will not go through all of them. It's probably most interesting to understand what the result says rather than looking at the details of the proofs. There's something in the chat? No.
It's the AI chatbot.
Okay. AI is asking us for something. Okay. So finally, toy examples, toy experiments. So the question that we then ask is, okay, we have this expressive power results, differences in expressive power, but how is it in practice? If we have some experiments, can we actually see this expressive power differences, or maybe in practice it's completely different than in terms of theoretical results? So what we did is we directly implemented both global and local MPTGNNs without a lot of thinking, without a lot of optimizations, just in a straightforward way. We are not trying to beat some benchmarks. We are not trying to compare with others. We are trying to compare global and local MPT-GNNs. This is the goal of this experiment. We tested it on TGB 2.0, and we looked at three sets, so TGBL Wiki, Review, and Coin. You have statistics there of those. All of those are link prediction tasks. And as you can see, the number of nodes and edges increases, and the numbers which you can see in the table are those which we were working with. In these benchmarks, edges are also labeled. They've got some features. We just discarded them at all, because in our setting, we are interested, at first at least, to look at temporal graphs without edges at all. And we did experiments using the protocol in TGB. In particular, we looked at MRR. And what we observed is that in all three data sets, local message passing is a little bit better than global. I mean, the results are not great, of course, but again, we are not trying to achieve something high. We are trying to compare local and global, and we see that local is always better a little bit than global, which corresponds, if you remember, to our picture in a sense that if I have color persistent temporal graphs at least, then expressive power of local mechanism is higher than global. So at least in this toy example, in this toy experiment, we can observe some similarity. It does not mean that it always is like this, but in this case, it happened to be like that. And we also did another experiment. So we were wondering how the number of layers, so how the number of iterations of message passing mechanism impacts the performance. And we did it for Wiki dataset for both global and local message passing mechanisms. And you can see graphs plotted on the slide. So I think one interesting observation here is that always this global message passing mechanism is below local, no matter how many layers we have. Another is that the number of layers that we needed, at least for this data set, is not big, it's not huge. So the maximum is maybe around 6 or 7 for local and for 5 in the case of global, which is somehow dependent, of course, on the data set, but similar to standard GNNs in which not too big number of layers is enough. And another observation is that these local mechanisms can have bigger number of layers to have higher performance, whereas the performance starts dropping if you have that high number of layers for global mechanism. We don't know why it is the case. We don't know if this is dependent on this data set. This is the observation that we made. I think this is also interesting to study more.
Do you think this is because the global message passing causes more over squashing because you keep bringing up basically stale embeddings from previous step, and then you kind of bring it forward to future timestamps in a sense, but I'm not exactly sure.
So I know that Michael was doing some experiments with that, and he also was looking at this problem a bit. I don't know if you have, Michael, and any comments on that, and if this can be the reason.
That would be precisely my explanation, Andy.
Okay.
Because there's this second temporal aspect where you are training your model through time, so the embeddings are also stale. This is more pronounced in the global setting. There's more old stuff going on. So if I had to guess, I think it would be that.
Mm-hmm. That makes sense. Yeah, thanks for the explanation. And I think to me, I'm not so I think like it is surprising that local is better than global, but also in a different sense it's not, because local respects more the timestamps when these things happens in a sense, while the global is kind of discarding the timestamps when you are kind of putting past information into the future, right? So it doesn't really matter where your current timestamp is, you are going to bring past information from there to there, right? So in
That's
that
true,
sense, but yeah.
I'm not sure if maybe from what you are saying, I have a feeling that maybe you read it differently that we use it. So for us, global is the one which uses the time point in which the node occurred. and local does not. So local only looks at the single snapshots, and the
Right.
global can pass message from the old snapshots. Is it according to your understanding?
I was just thinking about the visualization you were putting because the local is sending messages within the snapshot when the message happens, while the global one is kind of has, for a lack of better word, like temporal connections to past when it brings the information over.
Yeah, that's exactly. So I thought that you maybe.
So that's kind of what I meant, yeah.
Yeah,
Yes, but to me that seems like a feature because in some way you are providing much more context on how things are happening. So from time step to time step, you are looking into the evolution of the graph, and eventually that evolution of the graph is the one that provides you like much better understanding, like how things evolve and better results at the end. Make sense?
And also another way that, so not sure we want to get into too much discussion here, but just one last point on this, is that you can also think about scenarios where the timestamps are shuffled, right? And what happens with global and local. So it will affect local a lot because a lot of message passing just simply will not happen at the same time. And then global, I think it's less affected. I'm not sure, but just conceptually, I'm thinking about it. Maybe it's a bit less affected.
That's a good question, but then probably would have to at first specify what does it mean to apply global and local mechanism on shuffled date time points. It's not that clear to me, but I think that that it would be more problematic for the local message passing mechanism. We didn't consider this. Again, we looked at the most basic setting to understand what is even happening, because even here it seems like not clear from the first sight what is really happening, which is better expressively and
Definitely, super interesting. Yeah, thanks.
May I ask you just a question following up on Andy's comment? When you mean like this kind of shuffling, you mean that like you just take any kind of time step in any order, but still like in this global view, you will assume that all of the context provided for the global one, it was time ordered in a particular way. Is that right or not?
I mean, we didn't consider shuffling at all, so I don't know if this is the
No,
question.
I mean, my question was to Andy. My question was to Andy, just to understand how he thought about the problem, not to this particular.
Sorry, can you repeat it again? I was like reading the message.
Yes, when you mentioned this kind of shuffling, you meant that like the graphs that are being provided are not following temporal order. But if you will have this kind of global approach, in some way you will require that the global representation was time ordered. Is that right?
Kind of. So what I mean by shuffling is that you have timestamp T1, T2, T3, and you have the same set of edges that will happen, but the timestamps of which they happen are shuffled. So let's say the like edge from A to B are now happening at time 2, like versus time 1, and you are kind of perturbing the temporal order of things. So this would affect the local message passing more because some of these nodes will just not be reached at all because the same two edges don't happen at the same time anymore.
Okay, everything
In
clear.
that sense.
Thanks.
Yeah.
Thanks. Yes.
And another thing which I don't know comes to my mind from this discussion, it may be interesting to actually do some shuffling of the snapshots in a way that I take some snapshot and I put it, I don't know, it was time point 50 and now I make it time point 20. So I reorder some stuff like that, and that it may be interesting to see how it impacts those models. So it should have impact on those models, right? We would like to have it an impact because the time order of events should impact the representation, the internal representation. So seeing what kind of types of shuffling make what impact would be interesting also to consider. But this is again something we didn't consider there at all. And actually, let me conclude because this is all I wanted to say. So it's nice that we actually started this discussion now, but let me finish by saying that, yes, so we introduced the way to study expressive power of this message passing TGNNs. And our tool is that we construct knowledge graphs and apply WL, relational WL on these knowledge graphs. And this allows us to study expressive power we show, for example, that expressive power of global and local mechanism is incomparable. And on color persistent graphs, local are strictly more expressive. So those are, let's say, two main results from the expressive power point of view. And it seems that experiments are somehow aligned to these results. In future, what is interesting to study, I believe, is first of all of ideas that you mentioned and going to more general settings and so on. But other thing which I find interesting is to look at different notions of expressive power. So this expressive power notion here is about distinguishability. So is there a model which will allow me to distinguish these two nodes? But what is probably more interesting in many scenarios, at least, is to understand what kind of function can be encoded by GNN. What kind of property this GNN can express rather than what it can distinguish, and this is completely different notion. And this in GNNs was recently studied and is recently studied in terms of logical languages. So what I find interesting is to find out if there is some combination, some relation between this message passing TGNNs or other TGNNs to temporal logics. And finally, before I thank you for the attention, let me make a small advertise. So we will have in London, August or September, we are still deciding this conference called Time. So please have a look at it. We will have some call for papers, hopefully not too far in the future. If you have any work on temporal reasoning, this is more on logical and formal methods, but also a lot of neural stuff. If you want to come to London and meet, I think it will be a nice event. So thank you very much for the attention. And if you have any more questions, I of course open.
Yeah, so we still have a few minutes for discussion. So feel free to ask your questions in the chat or unmute yourself. And yeah, so thanks so much for the very excellent presentation. So you can tell from the discussion that this is very good presentation and people are like understanding the material and so on. So I do have more questions because there's a lot more things to discuss for temporal graph, like obviously, but I think in terms of how you define isomorphism, I was thinking that your current way of definition can even be pushed further. So in some earlier papers, people even just get rid of timestamps and just preserve the order of the edges. So this is an even stricter version of isomorphism, right? So you are removing even more temporal information, and in that sense, you can maybe derive a different set of like results, or stronger results or something. And kind of to your other point before about like playing with the edges and the snapshots and so on. So in our like recent paper that I presented like yesterday at the log conference, we talk about the UTG framework, but the high level like idea is that sometimes for practical like applications, you might not want to be operating your predictions on kind of this very fine-grained time granularity, like second-wise input, like T1, T2, T3, T5. You might want to be grouping things into snapshots for faster efficiency and so on. But then when you take a temporal graph and you reprocess it in the sense that so you are grouping like edges that are close to each other into a same snapshot, then you are also losing information. And one thing that we didn't really like explore in that paper is that when you discretize the graph in that sense, you also start to induce isomorphism in the graph. So because as you see that the time information gets lost, gets more compressed, the graph snapshots start to look more and more similar potentially. Not even across temporal graph, even within the same temporal graph. You could have a bunch of triangle snapshots and then they all look very similar to these kind of three users that always have these messages. And then you're then what happens with your GNN? Like does it still capture the differences between them? And so there's a lot more interesting following work on.
Yeah, I think that's very, very good points, and I really like them. And so we were started also looking at these different types of isomorphisms, and the one that you mentioned exactly, that you have only time order of time points. So for me, when I think about time, there are these two components, right? Order of time and metric components, so distances. And then when you play with those, if you have more of those or less, so for example, only order but not time distance, then you obtain a different type of notion of isomorphism. And maybe you can have also some GNNs which are specialized also only for this setting, so they do not look at the time distances. Notice that those message passing mechanisms that we considered here look at time distances. So time distance is important for them, but maybe you can have some weaker ones which will only look at order. And in many cases, I think this is important, relevant, and enough for us to model some cases. So yeah, I think this is a lot of interesting stuff to look in terms of this isomorphisms. I agree.
There's a ton of question in the chat, and I think Pharma, you also have a question, so maybe you want to go through them like quickly.
Yeah, I just wanted to mention that, I mean, to me, like the result on the wiki is very interesting, and it seems like the global somehow helps the over squashing, while the local helps the recency bias. And that could be why we see better performance with the local on wiki, because we saw that there are a lot of like new edges at each timestamp. But I don't know whether that makes sense to you or not.
Yes, I think makes sense. And also, I think in general, those local should be, again, this is probably a question to Michael, but I think it's much quicker, or at least quicker to compute it. So in terms of computational behavior, it's quicker because the number of edges just should be smaller in general.
Yes, yeah, it's certainly at train time it's much faster to compute. And as Farimir says, it does depend a lot on the data set. The Wikipedia example probably favors this recency bias aspect. So it could well be that a different data set would favor a global approach. I would just struggle to think of when that would be.
So I will also quickly read the questions in the chat. I didn't mention, could you explain more about possible relations to temporal logics?
Yes. So I don't know what are these connections, if there are any proper connections. This is a future work. But the question would be in correspondence to the first future work part. So there are many logics and many formalisms which allow us to say what kind of temporal properties can be expressed on graphs, not by learning just from the formal perspective. So then the question would be, is it the case that I can construct some logical language, some set of logical formulae, some formal language, such that it will correspond exactly to those properties which can be detected by TGNNs or some type of TGNNs? If we have something like this, I think it would be very interesting because we exactly know what kind of properties can be expressed there. If we want to express something more complex, it means that the TGNNs are not enough. We need to add some expressive power. So to find such a relation, I think it would be interesting. How this relation would work and with which temporal logics, this is a question. It's not clear to me. In case of GNNs, we see that this two variables fragment of first order logic is important. So maybe some kind of two variable fragment of some temporal logics would be something interesting to consider there. We didn't start, so we don't have any results on this, but this is at least the idea that I had while writing these future work points.
And there is two more questions actually. The one is that, do you have any intuition example of the time isomorphism? And the other question is whether the conclusion from homogeneous graph applies to heterogeneous graphs.
Okay, so do I have any example of isomorphism? I mean, I don't exactly know what is the question about. So we have these two notions of isomorphism. If this is the question about definition of isomorphism, then this is the definition that we found in literature, a time-wise isomorphism, and this is the one that, point-wise isomorphic is the one that we found in literature and which seems very intuitive to us. And the other is this time-wise isomorphism, which is our notion. And as Andy was saying, there are also more. So yes, there are several of them in literature. So if this was the question, then probably it's easy to find them in some papers. And yeah, the homogeneous graphs to heterogeneous graphs. So is it a question about expressive power or in general in our results? I don't know. I have not clue really. I would have to consider this and see how does it work from theoretical perspective for expressive power. We didn't look at more complex types of structures. And of course, we didn't do any experiments, so I don't think I'm able to answer this question. We don't know. It's an interesting question to look at different extensions of structures, but we didn't do this so far.
So I don't know whether there is any other question, but thank you very much for the great presentation.
Yeah, thanks for the great presentation and thanks for the very engaged discussion, everyone. So we'll also put the recording on YouTube, and then if you would like to share your slides for definition that people want to check, and then you can also share with us, and then we'll post on the website.
That's great. That's great. Thank you very much. And yeah, if anybody does some research in a similar direction, please, you can contact me. I'm more than interested to collaborate on this expressive power and not only results of message passing. It seems to me very, very interesting direction. Thank you very much for inviting me and for the very nice discussion. Thank you.
Thank you very
Thank
much.
you very much.
Thank you. Thanks, everyone.
Thank
See you.
you. Bye.